So I want to do some exercises in, given a description of a query, write both an SQL query for it, but also write the query in relational algebra. And so I've pulled up over here dbeaver, and hopefully you watched that other video I posted that talked about whether or not to use dbeaver. I've already set up my SSH tunnel. I'll probably test that out here. Let's try running a test query. Okay, so hit Control Enter, see what happens. Looks like it worked. A common exam question, one that you'll have to get used to at this point in the course, is here's a description of a query, like this one. Write the same query both in SQL and relational algebra. And of course, there are also questions like here's some SQL, give the relational algebra. Here's the relational algebra, give some SQL for it. So what I want to talk about, and we'll spend quite a few other videos writing SQL queries. So this will be one of the few that really talks about relational algebra in examples, besides what we do live. When we write SQL queries, there's a certain design pattern that we follow, and it's akin to how you learn how to debug in CSC 110 or 111. It's one thing to write 30 lines of code, but it's another to write the code in a way that when you're done all 30 lines, you have a reasonable chance of it being correct. So our goal here is to, given a description of queries, write both SQL and relational algebra. And there's some notes just about like what the usual evaluation expectations are for queries. Generally speaking in this course, unless you are specifically told to do so, it doesn't matter what order the rows of your result appear in your query result. And that's because in the relational model, the result of a query is a relation, which is a set, which doesn't have any internal ordering. SQL does have operators for ordering the results. We'll see an example, sort of a teaser for that at the very end of this sequence. It is also the case that if you're asked to, for example, select a customer name and order date for an order, you are expected to select only that. If there's extra columns in the result, even if they don't seem to affect the validity of the result, it's wrong. So the projection operation in relational algebra, that is an important outcome of this course. And so if you're asked to retrieve a specific set of data, it is significant that nothing else appear. And unlike for rows, it is expected if you are asked to retrieve a certain set of columns that those exact columns appear, and they appear in the order that they're given if an order is provided. Here it just says customer first name, customer last name, and order date. I would expect it's good to provide them in that order. What I would encourage you to do over on the side, I'm actually doing it literally right now because I forgot, is to pull up in some other window the second slide of the SQL and relational algebra lecture, which gives the tables from this database. So we're using the basic fruit database still, which has those three tables: products, order contents, and orders. And it's probably pretty helpful to pull that up on a separate window or something so you can look at it, because as I've mentioned, it's sort of hard for me to keep that on my view when I'm capturing my screen. So let's just start running through this. I'll begin by, maybe we should alternate between writing relational algebra first and then writing SQL, or vice versa. So retrieve the customer name and order date for each order. So I want to slowly begin to model what I think is a good query design process. Now in this case, you probably have, you can pull up the orders table on the side, but if you want to remind yourself what the customer name looks like, you could always just run a quick query that examines the table. Okay, so I've got two columns: customer first name, customer last name. Now a disclaimer here, on exams I will make sure to give you column names that are short enough that they don't make your relational algebra too tortured. I'm going to phone it in a little bit on this lecture, which is that I'm not going to write out customer last name. I'm going to instead write out last name where it's unambiguous. On an exam, you would generally be allowed that as long as it's clearly, it's very obvious what you mean. So what I want is just the name and order date for each order. So I'll start, I guess I'll write that, I'll start by writing the relational algebra. So question 1. Okay, so my relational algebra is, I'm going to start with my set of orders, and I notice the orders table, which is what I've printed out here, does have all the information that I want. Order date, customer first name, customer last name. And I want them in first name, last name, order date. That's the order I want, but that's all I need. I don't need any other tables, and so it's sufficient in this case, I think, to do a projection. So I'm just I'm basically eliminating that order number column. So I'm going to keep first name and last name and order date. And I'm going to use as my input the orders table. And how do I write that in SQL? Well, we already saw that the projection operator in SQL is the column selection clause. So I would do select customer first name, customer last name, and order date from orders. And I've mentioned already that the exact format you use to indent your queries, you are welcome to use whatever format you think is readable or whatever. I use a pretty idiosyncratic format myself, and it's also unlike a lot of other languages I write, I'm not always consistent. There are times I put a query all on one line. There are times I split it up into multiple lines. So we'll try running that. Take a look at the result. On assignments, because the queries are typically pretty tough, we often give you a one sample output, so you get the result of running the query on one database to give you some calibration. But the ability to know if your query is correct, so to test it, even if you don't know what the answer is supposed to be without running the query, the ability to investigate that and validate it is an important skill to build, and it's an important outcome of this course. So I look at this and I think, based on what I know about my data, by looking at it myself on the side, it does look like the right answer, and so I think I'm done query 1. And in this case, I didn't do much work in terms of relational algebra either. I just did a projection. I just eliminated some columns. So we'll just get that out of there. And then up here, we'll scroll down to query number 2. Retrieve the order number and nothing else of every order that contains at least 5 kilograms of any single item. I'm going to write the relational algebra for this first too, because I want to prove a point about the way SQL works. So I think, okay, I need the order number and the weight of an item. I don't need the price of the item or its name or the name of the customer that ordered it. And so maybe look over at your other window. It looks like maybe what I'm looking at here is the order contents table. And dbeaver is helpfully trying to autocomplete, but it's doing it with a font that's almost probably impossible to read. Okay, there we go. So there's my order contents table, and I notice that, yep, it has order numbers, and yep, it has kilograms bought. And that's all I need for this query. I need to know how much of each thing I bought. What it's asking for is, I want to find every time somebody purchased an item which weighed individually more than 5 kilograms. So actually it says at least 5. That includes 5. So there's order 1002 contains 2 items of weight greater than 5. Order 1001 contains something with 10 kilograms. But it's not saying the total weight of the order. It's saying if any single item has weight that is greater than 5, I want the order number of that. So I think I know what I have to do here. What I want to do is I want to pull out all the rows. I want to keep all the rows that have a kilograms bought of greater than 5. And then I want to just keep the order number from the result. So I'll write the relational algebra, and then I'll step through the query that I write in a bit of a slower order, because maybe we can show how we would debug this. So I think the first thing I'm going to do is I'm going to strip out, I'm going to filter the rows by the kilograms bought. So I'm going to keep all the rows kilograms bought is greater than or equal to 5, and I'm going to start with my order contents table. Oh, and this is Q2. And then I'm going to take the result of that, and I'm going to project it, because all I want to keep is order number. And just to be clear, if all you have is this, you will not get full marks. It doesn't matter that, yes, the thing you want is buried in there somewhere. All you need to do is remove columns. Removing columns is part of the question. So I keep this. And then once I'm done, I should have a set of order numbers. And we know it's a set. The projection operator gives us back a set. And so this weird remark about no duplicates appearing in the result, that's taken care of. The relational algebra operator takes care of that for us. But maybe we can observe it may not be the case that the SQL operator does. So I'm going to start, okay, select star from order contents. So I think, maybe I'll do some housekeeping here. We'll put that on its own line. I think what I want to do is I want to just keep the cases where the number of kilograms bought is greater than or equal to 5. So I'll run that. I mean, I'm not done yet, but I'll run that. And I look at this and say, okay, so yeah, order 1000 doesn't contain something of weight 5 or greater. Order 1003 also doesn't. So order 1001 and 1002 both do. But we notice that there are 2 rows for order 1002 here. Okay, well, that's fair enough. But if I just strip off and keep the order number column, then I do have the set of order numbers I need. So we'll try that, because we don't need the other data. We don't need product ID. We don't need kilograms bought. So I'll run that. And I notice, well, the SQL select statement doesn't eliminate duplicates by default. When you do a column selection, it doesn't go through and make sure that everything appears only once. And so this is still incorrect. It's very close to being correct. If this is an exam question with partial marks available, you're almost there. But we need to make sure that there are no duplicates in the result. And it's interesting that this does not, although this almost matches the relational algebra in terms of where the clauses are, we are still missing the relational feature of that projection operator. And so there's actually quite a few solutions to this. This one, I think, is the easiest one. If I put the word distinct after the word select, after the query is over, at the very last stage, it goes through and eliminates any duplicates. And the reason that's not done by default is because maybe you don't care. Maybe it doesn't matter if there's duplicates, and you can maybe see that if there were 10,000 lines coming back from this query, going through and eliminating duplicates requires some logic. It could be an n-squared calculation, or there could be some sorting involved or something. And in any case, we want to avoid that if it's not necessary to do that. So I'll try running this query. And now I can see that it's printing the order numbers without duplicates. Interestingly, the rows came back in a sort of counterintuitive order. I don't know why order 1002 is before order 1001, but notice that it doesn't say anything in the question about the sorting of the rows. So there's no requirement that they be sorted. Not that it's relevant to this series of examples, but just as it'll come up again later. We do actually have a clause we can add at the very end to force the sorting of the rows. So I order by order number ascending. Now you're welcome to do that. You won't lose marks for adding one of those, but you shouldn't feel obligated to sort your rows in the same order that we do unless we specifically tell you you need to do that. Okay, so I think I now have both the relational algebra and the SQL for this example, so we can move on to query number 3. It's interesting. This is something you can think about later when I'll post this the text file itself. There are ways of doing this without the distinct qualifier. One of the most accessible, I think, is using grouping in a certain way. And if you know enough about grouping to figure this out, that's a very good sign. Okay, so query 3. So I'll just get rid of that. That's a weird looking 3. Try again. That's a little bit better. Query 3, retrieve the name of every product ordered by this customer. And it points out, and this is worth considering, when you're asked to construct a query given a schema, so here are 3 tables, products, order contents, and orders, construct queries on this, it is assumed, unless you're told otherwise, which you aren't, it is assumed that your queries should work for any possible way of realizing that schema. So that is, the tables and their columns don't change, but I should be allowed to change what orders exist. I should be allowed to add 1,000 new orders. I should be allowed to delete all of the orders or add customers or products or whatever. And your query should still do what is being requested qualitatively, which is find all of the products ordered by this customer. It's pointing out that at present, that customer only has one order in the system. But that doesn't mean that you can write a query that is constrained to, let's say, that one order, or to the idea that this customer only has one order. You may notice that you could look up yourself on the side here that Fiona's order is order 1002, and therefore you could just look up order 1002. So the question is saying you cannot do that. You have to make sure that you allow for there to be multiple orders, or for you not to know what the order number is. So how do we tackle this? We know that we need the product's name. But we also need the name of the customer. We're working with all of that stuff, and we don't have those two things in the same table. And in fact, there is no way of using just the orders table and the products table to achieve this either, because in the middle, we need to know, what were the products in each of the orders by this customer. And so it looks like we actually need to use all 3 of our tables somehow. I should also add that unless it's, in this context, I'm going to interpret this to mean that each name should appear only once. So retrieve the name of every product ordered by this customer. I would interpret that to mean I just want the names of all the products. I don't want to see the name Lime 10 times. I think I actually might make a modification when I post that. That is something on an exam or an assignment you would be free to ask for a clarification there. So what I guess the first thing I want to do is I want to say, how do I tackle this? We'll write this one SQL first. Okay, I guess the way I would handle this is top down. I would say I know one thing that's fixed. That's the customer's name. So I know that it's going to be about this customer one way or the other. So let's get all the orders from this customer. And in SQL, the string equality operator is just a single equals sign, and we typically put strings in single quotes as a matter of convention. You can use double quotes in some cases too. Okay, so I'm just going to run this. I'm not done. I'm not even close to done. Okay, so that lists all the orders from that customer. And notice that there's only one of them, but you need to be writing this in a way that doesn't assume that. But it does list, that is all of those orders. Okay, so now I need to know all of the products in all of their orders. But I obviously don't, I guess I have this table order contents that I can use to map the order number to a product ID. So I could do natural join orders with order contents. And we'll try running that. Okay, great. So now it includes the order number and the product ID and how much of it was purchased. So now I need to actually have the product name when I'm done. And I don't yet have that, but I finally have something I can use. I have a product ID. So in fact, I can take the result and I can join it again. Join orders to order contents, join the, and natural join is a two operand operator. By default, the parentheses go in just like addition. We do the first two things first. So we could use brackets if we want. We don't have to. I join all three of them together in that order, and then we'll see what happens. And we notice, okay, so it's a good thing I've got dbeaver. This would look pretty ugly on the command line. There are the product names. It's just called name. In my relational algebra, I'm probably going to say product name to avoid too much confusion. But we notice we have everything there. Now what it says is just give me every name, and that's it. Okay, so I'm going to select name. I'm actually going to rename the column to make it very clear that I mean that it is a product name. So do Control-Enter, product name. And then just to polish it off, although this doesn't indicate it, I might lose a mark if I assume that I'm always going to have distinct product names. So if I do select distinct, I'm avoiding that problem. We run it again, nothing happened because it was already distinct. Okay, so how do I write this in relational algebra? Well, we've noticed already that because of the way SQL statements work, without nested queries or anything, the from clause is what happens first. And so we sort of expect that's going to be the thing on the very inside of my brackets. So I'm going to write that over here. So orders, natural join, order contents, natural join, products. Okay, and then I take the result and I filter it by this particular customer first name and last name. So that's going to be a pretty ugly sigma, but I do a search. So I'd say first name, I'm going to have to, I forgive you if you do the thing I'm about to do on an exam. I'm going to have the subscript run all the way underneath. You need a certain artistic talent to know how to space text. Okay, so first name is Fiona and last name, and then I guess I should use single quotes for both. And then I take the result of that, and this is important. You'd lose marks for not doing this. I have to then make sure I only keep the column I care about. So I project out product name. Now, the name of the column formally is name. Now, on exams, usually we give column names that are magnanimous to both relational algebra and SQL, this database we've been using for lots of other things. It's okay to use little abbreviations in relational algebra like first name instead of customer first name, as long as it's absolutely clear what you mean. There's no other first name that could be confusing things here. So I think this does give me everything I need for this query. And we're noticing the relational algebra piles up, and it is notationally a bit ugly looking. There's a lot of space that we don't need, and these subscripts pile up. On the other hand, it is a much easier and more methodical way of breaking the query down. The select statement is in such an odd order that it makes it sort of hard to see what's really going on. So let's go down to query number 4. Retrieve the total weight sold of each product. The total weight sold. So in this case, it's saying it wants the product ID and the total number of kilograms. That's how I interpret weight in this case. The total number of kilograms of that product that are sold. And if you look on your on the database on the display of the tables, you can see that. The order contents table actually contains all of that stuff. If all I need is the product ID and the number of kilograms purchased in total, what I want to do is some operation on the order contents table. I actually don't need, because the products table contains the name and the price per kilogram, I don't need the products table because it doesn't give me anything I don't already have, product IDs and the number of kilograms bought. But I do need to find some way of generating only one row per product ID. So for example, product number 3, I purchased, let's see, it looks like I've got, there's 10 kilograms of it there, plus 0.6, plus 3, so 13.6 kilograms in total. So I want to aggregate the rows of this table, grouping them by product ID. So I guess I'll start with that. So let's see, select star from order contents, group by product ID. Let's just see what happens if we run this. And it says, I'm sorry, what are you talking about? If I'm trying to select everything in order contents includes a bunch of columns I'm not allowed to use. So I'm not allowed to, product ID is my grouping criteria. Order number and kilograms bought, if you think back to the lecture about this, unless those are aggregated, you're not allowed to take them out of the group. You're not allowed to use them. And so if I do select star after I've grouped, it'll say you can't use order num and you can't use kilograms bought. Now you might have to actually run this yourself to see the error. It's a bit small, but it says, group by product ID. Nope. There we go. And you'll see it says order num must appear in group by clause or be used in an aggregate function. That's because this star is trying to bring in order num. Now I'm allowed to use product ID because it is one of the grouping criteria. But if I, just to drive it home, if I try and bring in order number, it says, sorry, how can you use that? There are multiple things in each bucket, multiple values of order number. Which one do we use? So in any case, what I want to do is I want to sum up the number of kilograms bought. Kilograms bought as total weight. And so the sum aggregate function allows me to add up, I first group all the rows by product ID, I make a bucket for each product ID that I see, and then inside each bucket I sum up the kilogram bought value, and I call the result total weight. Let's just space that a little bit more. Okay, so that's one thing, but how do we get this in relational algebra? So we know we need the gamma operator here. And we don't do anything else besides use gamma and then some renaming. And we notice, if you remember the lecture about this, we can do the renaming in the gamma operator. So I start with the order contents table. I know that. Okay. And then I feed it into the gamma operator, where I use as my grouping criteria, that's the bottom, I use product ID. And on the top, I give my aggregation function. And I'm allowed to rename it as I give it. So I'm going to say total weight equals sum of the number of kilograms bought. There we go. The result ends up containing the two columns that I want. So there's actually no need to do any more work. Now there's one thing, I'm only noticing this now. This other requirement, I meant to talk about this, but I glazed right over it. Do not include products that appear in no orders. Now you might notice that there are 6 different products in the products table, and only 4 of them show up in this result because nobody ever purchased a pineapple. And so it doesn't show up in the result because we were aggregating a table full of the values of product ID. This, what I've highlighted here, gives me an escape. I can just say, well, I wasn't supposed to. I don't have to include the products nobody bought. But we should be considering that warning as sort of ominous, because maybe there's a time, and it might come soon, that we do have to consider, what about products that don't appear in order contents at all? We still need to know. I mean, if we're taking inventory, I might still want to know how many pineapples did people buy. But for now, this is actually all we need. So I take order contents and I group it and aggregate it to get the total number of kilograms purchased of each thing that appears in that table. Now, if I cared about products that nobody bought, I'd have to do something else. Okay, let's take a look at query number 5. And I'm going to cheat with my relational algebra here. And I'm going to leave it up. Okay, query number 5, let's compare the two of them. Query number 4 is retrieve the total weight of each product. Okay, query number 5 is retrieve the total weight of each product. Do not include products that appear in no orders. Okay, good. The result should contain 2 columns. This time it says product name and total weight. And I think to myself, well, that's going to be an easy one. We'll just start by copying and pasting. So we've got this, and I got my relational algebra for it. What does it not give me? Well, it gives me product ID and weight, but it doesn't give me product name. So the question is, how do I get product name into this? And there are two answers. So one of them would be, hey, you could join, and this is a bad idea, don't do this, you could join order contents to products. And just to be clear, if I do that, I'll make a test query. If I do that, then I end up with a bunch of rows that contain order numbers, kilograms bought, and names. So I could think, hey, if I do that, I now have the name of each product. Why don't we just group, oh, I don't know what happened there. Why don't we just group by name and then select name? So does it work? Well, it does give results, sure. Do you get full marks for it? And the answer is no. You don't necessarily know, although it would be a bit bizarre in this case. You don't know that there aren't two products with the same name. Why do you have a product ID? That's the key for the table. Why do you have a product ID if all the names are unique? So you shouldn't in general try and assume that name is unique. Now in this case, for such a simple query, you might be given the benefit of a doubt on an exam. On an assignment, likely the reason the query is phrased this way is to catch you and make sure you don't fall for that trap. If I want to identify a product, I should use product ID. That includes for aggregation. I don't know that there aren't two products, hypothetically, that have the same name. Okay, so that brings us back here. Now, just to be clear, the version I just wrote that I said was a bad idea, that still would get you 4 out of 5 or something. That's almost all the way there. But we need to defeat that mentality quickly, because if we don't internalize this issue soon, when we get really complicated queries, it's going to be really hard to pick it up. So what I want is the total number of kilograms bought of every product. And I want to make sure that each product is distinguished uniquely. And the best way to do that is by product ID. So now I've got this table that gives me, for every product ID, the total number of kilograms that were purchased. But what I want is the name of each product and that value. Well, hey, I've got a table full of names and product IDs. Why don't I join it to this query result? I know that's an odd thing. Where am I getting that from? But keep in mind, anything you can compute, that's a table. And anything that you need in a table, if you can compute it, you can join it just like anything else. So I'm going to say select name and total weight from products, natural join. Actually, we'll put those on separate lines. And then I'm going to join it to this thing. I'm just going to space that so it's more uniform. Okay, so I'm going to first compute this table of product IDs and the number of kilograms bought. And Postgres requires you, whenever you use a nested query, you have to give the nested queries, like the table you produce, a temporary name. So you have to say as something. You don't have to use my convention, but I always just use like T1, T2 if I don't want it. I'll show this off and then we'll see what happens if I break it. So what I'm going to do is compute the table I have below, join it to my products table by ID, because that's a column they both have in common, and then pull out of that the name and the total weight. And so I get this. Just to be clear, if you do a nested query and you don't put a name at the end, Postgres gets very upset. It says it must have an alias. I will, over this course, probably make the mistake of leaving it like this. You will see this error on my videos over and over again. It became so bad last time I taught this course that at some point we had to make up a little jar with we could put coins in, and every time I would make this mistake, I had to put money in the jar, and that did help quite a bit. I still have that jar somewhere. So if you get that error, don't worry about it. It's just Postgres saying you have to give everything a name. Even if you never use the name, you do have to give the nested query a name. So I'll run that. And that gives us our result. And then the question is, what's our relational algebra here? And I quite sneakily, I left my previous answer up because I knew I was going to need to recycle it. So we've got question 5. No, it was an ugly 5. Question 5 here. So what I want to do is I want to take the products table and join it to this thing. and then I want to pull out of the result. So I'm actually I'm gonna put the join over here just to save some space. So I take that entire thing, the whole gamma result, I join it to products, and then I'm not done, because if you think about it, when you join to products, and we can actually verify this in our query. If I just join with products and then I select everything that comes out, I get a bunch of columns I don't want. I get everything else the product table gave me, product ID and price per kilogram. So I don't want that. I need a projection. And in general, if your column selection clause is not star, be very careful before omitting a projection. So I take this, put that whole thing in brackets. I'm going to project out the name, the name and the total weight. And there is a column called total weight at this point because I created it in the gamma operation. So I've got the projection, I've got the join. I think that is the complete relational algebra for question number 5. So we'll scroll down, we'll take a look at question number 6. Okay, retrieve the total cost overall of all orders by this customer. And so what this is saying is we need to find all of the orders that have this customer name attached to them and add up their complete total cost. What's interesting is there are two schools of thought. Like, depending on how your brain works, you have two ways of thinking about this. One way is to say, okay, so the database doesn't even tell me the total cost of each order. And you may remember from a lecture, we actually went through an example of how to compute the total cost of an order. So you could think, what I need first is a table that computes the total cost of each order. I'm going to run through this example. My real answer is going to be the next one, but I'll run through this. So how do I compute the total cost of each order? Well, I want the total cost by order number, so I'm going to select order number, and then the sum of the price per item times the number of kilograms of that item that is bought as the total price from order contents, natural join products, group by order number. So I use the sum function, and that's a good sign I probably want to use a group by somewhere. So we'll try that. And we can see that actually does give me the total price of each order. And if you think this way, you'd say, okay, how do I get the total price of all of the orders, all of them, because there might be more than one, all of the orders from this customer? Well, what I could do is I could join this whole thing. So we'll do that. We'll say select star from orders. Okay, the from might need to be on the next line. Orders, natural join, and then this whole thing. So I take a table I just created and I join that to the orders table, and I'll remember to give it a name. Great. And then we'll just take a look what we get from that. We'll press page up by accident too. Okay, so we do that, and we'll notice now we've got the total price of each order, and we have the customer who ordered it. So we could then take this and we could generalize it and there it is. So that's going to be all rows that correspond to this customer. Now, we actually aren't done yet. We then have to add up, because there could be more than one of them. We then have to add up the total price across all of those rows. And there are a few ways we can, and then only project out the total price. So I'm going to say select sum of total price as cost. The query demands that I call this cost. And it gives me this. Now, so just to remind you, that last step I had to take there was because there could be more than one order for this customer, and I can't assume that there's only going to be one. So I still have to sum up the total price column across all possible rows. Now, you might notice the query I just wrote, the sum total price, wait, I'm using sum, but I don't have any aggregate, I don't have any group by. The grouping I'm doing in here is irrelevant. How am I able to use sum? Well, if you don't specify a group by, you get one huge group of all the possible rows. So this is actually a correct answer. And what if you read the query carefully, it's asking something quite odd. It says, total cost of all orders by this customer. The output should consist of one column with just one row. So it's just going to be one scalar value. So this does the trick. but I want to write it differently because I want to observe something, which is that if your mind works this way, this is a great way of thinking about it. First, compute the total cost of each order, and then just join that to the orders table and match it up to the customer. But I might notice, hey, wait a minute. All I'm really doing is adding up the total price of everything this customer has ever ordered. So I don't need to first compute the order cost because the total cost of all their orders together is just the total cost of everything in all of their orders. So I'm going to approach it that way. I'll label these. So solution 1, solution 2. So I'm going to begin by first selecting all of the products this customer has ever ordered. So select star from, and we'll try orders, natural join, order contents, where, and then I'm just going to copy and paste this. I chose the longest customer name for some reason to use as my example. So I run that. That selects every order this customer ever, every product this customer ever purchased. Now, in order to get the cost of those products, I need to bring in the price per kilogram column. I've got the number of kilograms purchased, but I don't have the cost per kilogram. So I have to then take the result and do a natural join of that against products. So we'll try that. And now we have this monster of a row, which is going to be product ID and customer name, number of kilograms bought, the name of the product, and the price per kilogram. So I don't want that. I want to narrow that down a bit. What I want, I guess, is, let's see. So I would like to compute the total cost of all of these rows added up. So why not just do this? Select sum of price per kilogram times kilograms bought as cost. And I run that and I get the result. So what's interesting about this is crafty because I'm doing an aggregation with no grouping at all in the entire query, not even in a nested query. And that's because before I attempt to aggregate, I've already stripped out all the rows I'm ever going to want. I only want rows for this customer, and I want all of the rows for this customer. And if you use an aggregation function with no group by, the group is interpreted to be every single thing in the table. And in this case, that's actually what I want. Now, the other reason I want to do solution 2 is because that way, when I write the relational algebra, I can fit it in this small amount of space that I have. So I noticed that what I need to do is first I need to compute this big join. So I have to try and write small. There's my join. And then I want to take, eventually, I would like to aggregate with no grouping columns. So everything's in the same group. But I'm not done yet because before I aggregate, I have to make sure I only keep rows that I want. So I'm gonna use a sigma, and I'm gonna I wish I'd copied and pasted the sigma for this customer I already wrote. I still couldn't get it to line up. There we go. Okay, so now I've got only the rows for this customer, and what I want to do is take all of them, so I don't even need to do any grouping, really. I put them all in one big group, and I just add up the price per kilogram times kilogram bought, and I keep only the result. And that is actually the gamma operator. I am, everything, all the criteria is met, except that I have no grouping criteria. So there we have that. And I select, let's see, cost equals sum of, oh boy. Yeah, it's pretty ugly. And then down here, I have nothing. There's no grouping criteria. I could even like write in, there's nothing there. And this is query 6. That's a pretty weird sort of subversion of the usual logic, but it's perfectly valid. If you provide no grouping criteria, so no group by clause or an empty bottom of the gamma operator, then your grouping criteria is assumed to be that everything is in the same single group. So any aggregation you do will boil the whole table down to one value. So we're ready to move on to query number 7. Retrieve the name, so this is of course coming up again, retrieve the name of all products that have never been ordered. Okay, so never been ordered. So this is an issue I find people, and I mentioned already, set operations tend to bother people for some reason. It's interesting because there are a lot of misconceptions about what it means for a product to never have been ordered. And let me give an example of that. So I'm going to just write this in. I'll delete it before I post this, but just for the sake of the example. I want to select all products that have been ordered. Okay, how do I know that a product has been ordered? Well, it's in the order table. It belongs to some order in the order contents table. So I could start by this, select star from order contents. Okay, there are all of my familiar order numbers, products, and kilograms Bob. But I just want to know the products that have been ordered. Okay, it's this. Product ID from order contents. Okay, so that's all the products that have ever been ordered. Okay, great. I guess I could do select distinct. So there's all the products that have ever been ordered. And what's weird about this is that if I ask you a question like, find me all the products that have been ordered, this is typically what people would come up with. What if I ask a question like this? I ask you to give me all of the order numbers that contain product ID. Let's go with product ID 3. Okay, so I'd say, well, that's easy. I can use order contents for that. Select order number from order contents where product ID equals 3. There I have it. Order 1000, 1001, 1003. What if I ask the question, can you give me all orders that do not contain product ID 3? Here is the issue. People look at that and they say, if I want the orders that contain product 3, I go through and look for all of the tuples where the product ID equals 3. So if I want the orders that do not contain product 3, I just flip this condition. Nope, I just flip this condition around. We'll copy that. I'd say, give me all the tuples where product ID is not equal to 3. And we'll run that. And it claims that order 1001 doesn't contain product 3, which is false. Order 1002 doesn't contain product 3, which is true. And order 1003 doesn't contain product 3, which is false. This isn't telling me the orders that don't contain product 3. It's actually telling me the orders that contain any other products that aren't product 3. It could still contain product 3. And that's the issue, is that asking if something exists in this notation is easy. You go looking for it. To say that something doesn't exist, it's not sufficient to stand in one place and say, I don't see it, therefore it doesn't exist. You have to do something else. What you really want here is to find all of the orders that do contain product 3 and then delete those from the list of all possible orders. So we'll come back to this issue again. So this is, for the sake of relational algebra, that's not really the focus for today. I think my next video actually talks about this problem in more detail. But this is actually a pretty nasty problem for some people because I don't think it's that they don't get it. I think it's that they don't, their brain sort of short circuits and says, oh, that's an easy one. They don't think carefully about what they're being asked to do. So be careful if you see the negation anywhere in the question. If it says all things that don't have this property, it's not as easy as searching for cases where the property doesn't hold, because it might hold somewhere else. So here is a list of all products that have been ordered. So the question is, how do I know what products haven't been ordered? What I could do is I could take my list of all possible products, that is to say the products table. So here's select product ID from products. Okay, there's my list of all possible products. And here's my list of products that have ever been ordered. So how do I know which products haven't been ordered? Well, I just subtract one from the other. So I will use the except operator, which is the set difference. I will take the set of all product IDs and I will subtract away all of the product IDs that have ever been ordered. And I will actually delete this line because it's no longer relevant, this all products that have been ordered. And we can see product 6, product 1. That's what we expect. Now, a performance note here, you don't need to say select distinct if you don't want to. the select distinct eliminates the duplicates in this subquery. But because the except operator is a set operator, it will also eliminate duplicates for you. So you can omit the distinct and save the save the database engine a little bit of work. You don't have to do it though. It doesn't hurt to leave it in. Okay, so I now have a list of all the product IDs that go with products that have never been ordered. Now what it wants though is the name. I already warned you, do not assume that product names are unique. If you have to do work involving products, use IDs. Bring in the name later once you're done doing the work. So here I've done the work. I figured out the product IDs of all the products that have never been ordered. So now I'm going to select name from, nope, different, okay, from, let's see, products. When you autocomplete with this, it tries to give it a name. Natural join, and then I'm going to natural join with this subquery. And we'll have to give the subquery a name as well. All right. So see what we think of that. There is a list of all the products, the names of all the products that have never been ordered. Now you might, it's pretty wordy. There's a lot of stuff happening. What I was hoping to demonstrate by walking through this in a video is the design process I would use. It's usually pretty bottom up. I began by trying to figure out the core of what I wanted, and then I sort of slapped on new attributes as I got them. I first figured out IDs, then once I was confident in my IDs, I added in the name using a join. So what do we do for relational algebra here? Well, we might see that we've got a nested query now, which means probably we should work on this first. I take products and I natural join whatever this is to products. So I'm going to put this over here on the right-hand side. So I select product ID from products. Well, that is a projection. And I select that from products. And I subtract off the result of selecting product ID from order contents. Okay, I then take this entire thing, and I have to put it in brackets so that the minus doesn't get, like, the precedence is obeyed, and I join that with the original products table. And you might look at this and think it's sort of weird. I'm using the products table in several different contexts here. It feels wrong to join it back to itself. Well, welcome to the next month of your life. We're going to find that we work with these databases that have, in some cases, 1 or 2 tables, where we are writing queries that, in some cases, use a dozen subqueries, each of which selects from a table joined back to itself in some way. That's the way it works when you manipulate data. Don't think about this as joining products back to itself. Think about it as joining one facet of a product to a different facet. So I take this, I then do a final projection to pull out only the product name from this huge mess. I actually have to sort of nudge that over. There we go. And so that looks like the relational algebra for question 7. We're not done yet. So we have query 8, and query 8 ends on a cliffhanger, and we can scroll down and observe there's nothing left. Let's just get that on screen. So query 8 ends on a cliffhanger, which is try this. And we'll do that at the end. This is something we shouldn't need to ever say in relational algebra, sort them into ascending order. Relational algebra has no use for that because we should be working with sets. But we'll see that. And then in the next video, we'll begin talking about a few more things in SQL that don't really map onto relational algebra. Okay, here's what it wants. The total weight sold of every product, including the products that have not appeared in any order. And so if a product hasn't appeared in an order, then the number of kilograms sold is 0. So how do we figure this out? On an assignment, this would be valid. You'd be allowed to scroll up and kidnap some of your earlier code, so I'm going to do that. I'm going to start with, I'm not actually going to start with the product name version. I'm going to start with this, just to get us something. Okay, query 7, query 8. And I will also get rid of this. We're going to need to actually make this window bigger to fit the ugly relational algebra we need for this. Query 8. Okay, so this selects the product ID and the total weight of every product that has ever been sold. What I want is to somehow broaden this set to include the products that haven't been sold. Here's the way I'm going to handle that. I already know, because I tried this a minute ago, I already know how to get all the products that were never sold. I also know what their weight is supposed to be. And I'm going to try a thought experiment first. We already know that we are allowed, we'll do it up here. We are allowed to rename columns as we see fit. We are even allowed to rename columns using some weird expression, like price per kilogram times 10. I can make a column whose value is price per kilogram times 10. Am I allowed to make a column equal to price per kilogram times 0? Well, of course I am. In fact, you can make a column whose value is any expression. If I wanted to, I could make a column whose value is just flat 0. I would get that anyway with 0 times price per kilogram, but I can get it much more cleanly by just writing 0. So if I wanted to, I could concoct my own table with a 0 weight for every product. And the reason this is significant is, what I realize is all I really have to do to get the total weight of every product, including products that have never been sold, is take this thing, the result of actually computing for products that have been sold, and just mash it together with a 0 weight for all of those products that haven't been sold. If only there was a way to know which products hadn't been sold. Well, fortunately, query number 7 can help us with that. We'll take that and borrow it. It's actually this that I care about. I don't want the name, I just want the ID. So I already have this query to find the ID of every product that hasn't been sold. Let's take a look at this. So I'll run that. I'm going to put this back here. So this gives me the ID of every product that hasn't been sold. What I'm going to do now is take this query and use it as the basis for a sort of phony table that gives me the weight of every product that hasn't been sold. I'm going to select product ID, product ID, comma, 0, I'll call it total weight, from, and then I'm going to use this as a nested query. Although there are some tricks you can do to avoid a nested query, this is no time to be a hero. It's better to use a nested query here because you don't want the precedence of this operator getting in your way. So we have that, I give it a name, and we'll try running this. Okay, so there is a dummy 0 weight value for both of these two products that were never sold. And then here is a table that gives me the total weight of all the products that have been sold. Now all I need to do is jam these two big things together, and I get a table with the product ID and the total weight of every product, including products that have never been sold. And we know already we do have an operator for that, and it is union. So I try this. So now I've got a table with the product ID of every product and the weight that was sold, including cases where the product was never sold at all. Am I done? No, I'm not. What I was requested was product name and total weight. So I have product ID and total weight, but I don't have product name. So what do I have to do? Well, I guess I've got to take this huge thing, batch it up into its own nested query, tab that in, and I say select name and total weight. And you'll notice that in the union, both of the two tables I take the union of have columns called product ID and total weight. I've harmonized their column names. From, and I'm going to join this huge thing I just created with the products table. There we go. I run that, I see name, pear, total weight 5.5, and name peach, total weight 6.5, apple and pineapple, I have sold 0. Okay, so we have a couple things we have to talk about. You've probably been wondering for a few minutes how people can live in a world where we have to write queries this way. So there's a bright spot there. Well, actually, the point of this set of examples was to get to this level of query and observe that this is a little bit egregious. Although the query is well formed, and I would even argue we built it up in a way that was pretty methodical, it's no fun to look at, and it probably wouldn't be very much fun to actually deconstruct if you hadn't seen me write it. So I'm going to write the relational algebra, and then I want to talk a little bit about what we do about this problem in general. So now we know it works. I'm just going to scroll this up because we're going to need some space. Okay, so I want to build the relational algebra. I'm going to use the approach I did in the slides where I use multiple layers of relational algebra. I'm going to make multiple sort of pseudo tables. So we'll start, I'm going to use, I guess we'll call them, I guess R1 would be fine. Okay, so what's R1? R1 is going to be this subquery that tells me the alleged total weight of all the products that were never purchased. So here what I want is, I'm going to start by computing this. We already saw how to compute this, but I'm going to have to write it again from scratch. So I take product ID from products. I subtract off product ID from order contents. Whoops. Okay, and then I take the result of that and I apply a couple of transformations to it just to clean it up. So I only want product ID and total weight. Well, the only column I actually have coming out of this subtract operation is product ID, but I need to invent a fake column called total weight, so I'm going to use the row operator for that. I'm going to say total weight equals 0. So I'm allowed to rename the constant 0 to be the column total weight. And then that's R1. That actually was a lot less. Is there any way I can cram anything else into R1? Let's see. So one thing we might notice is that, okay, this view is not great for illustrating anything. Let's just sort of struggle a little bit to get that in there. Okay, so you might notice one of the reasons this nested query is so disgusting is that the join that I'm doing is between this whole thing. So the products table is being joined to this huge mess. And so it's not obvious that's the case because I didn't even indent as well as I maybe should have. So I'm going to go over here. I'm just going to clean this up. I'll put R1's definition a bit closer to its actual expansion here. So there's R1 gets that. Okay, so what's R2? R2 is going to be, I think naturally, I would probably take this whole thing. So I want to select the product ID and the sum of kilograms purchased as the total weight from order contents. I'm not doing much else here but aggregation. I'm just doing a gamma. So I'm going to select, I'm going to group by product ID, and I'm going to set, I'm going to call it total weight equals sum of the number of kilograms purchased. Great, and then I'm just going to pull that out of the order contents table. And we will call that R2. Okay, so we're moving along. I now have to take R1 union R2 and join that to my products table. And actually, we're almost there. So I would like to, my final result will be R3. Actually, we'll even, for the sake of finality, we will call it R final gets the result of selecting, projecting out name and total weight from products, natural join, and then what I have on top is R1, and then I union that with R2. So that's pretty ugly. And you might see that if we go forward and we keep writing complicated queries, we can't write relational algebra for all of them. And so the course, it's really important that we know relational algebra because we need to be able to model even this kind of query with it. But it is true that as time goes by, we're not going to require the more complicated things to be written in relational algebra. So this presentation and the lectures I've already recorded with the slides are pretty much all we need to know about relational algebra besides the tutorial style live stuff I'm going to do later. The next few videos are all going to be me writing SQL and not relational algebra, and it's going to get a great deal more complicated than this. So the question is, how do we live with ourselves? How are we able to write queries that are more complicated than this if this is already, trying our patience, the indentation's all over the place, it's hard to know what's going on, even if I write comments next to it or if I give descriptive names to things, like I could say as, I could rename this as products not purchased. Now, you might notice the name doesn't mean anything. It's just a good way for me to tell myself what I'm doing. Even if I do that, how are we supposed to figure this out? And so it turns out we have a few things that can help us. And one of the big ones, and I'll demo it quickly now, and we'll talk about it formally at the beginning of the next video as well. One of the big ones is we do have the ability to define temporary, we could sort of think of them as temporary tables. If we want to write a select statement, we can define our subqueries in advance to be sort of their own table, and then work with them as if they had been tables all along. And what we do is we use a statement called the with, well, actually it's not a statement, sorry, the clause, the with clause of the select statement. Before the word select, we are allowed to define our own sort of temporary tables to mean whatever we think is appropriate, like to anything we use often in our expression, anything that we think is cluttering it up that needs its own name, we can define it ourselves. So I'm going to do that. I'm going to pull out all of my subqueries, and I'm going to create them as sort of a stack of these temporary tables. So products not purchased. And actually, I'm going to say this is product IDs not purchased. And the with statement has the with clause has a couple of weird aspects. One of them is it uses the word as, but in the opposite way that we're used to. We give it a name, then we say as, and in the brackets we put a select statement. So I'm going to use this. And we'll put that there. You don't have to put it, you could put it right on the same line, just like anything else in SQL. It's your choice how you arrange it. But I'm going to do it this way. Okay, so product ID is not purchased. And once you put it in the with clause before a select statement, it becomes the same as a, oh wow, sorry about that. It becomes exactly the same as if it were a table that you were otherwise selecting from. And so we'll talk about this again in the next video, but I want to show that there's light at the end of the tunnel if we're trying to clean this up. So we'll try running that. Product ID is not purchased. The punchline of all this is it's better to use the with clause to begin with. You don't want to write a horrible query and then take it apart like I'm doing. That's not recommended. So here we are. I was able to conjure up this result. I will claim it looks similar enough that it's identical. And I can keep doing this. So I could say, here is the total weights of all the products that were purchased. So I could just take that and I could say, great, let's use our with clause and define something else. There we go, and it's pretty ugly looking. We'll just unindent that a bit. There are my weights of purchased products, and then if I want to union that, I have to say select star from weights of purchased products. I mentioned in the lecture about this that the strange way the union operator works makes it sort of difficult to use a union operator the same way we would use something like a join operator. So we have that, and we can see we're slowly pruning the query down. And so now what I could do is I could take this entire thing, and really this I think is the source of our problem here. This is a pretty ugly subquery. I'm going to start by removing this. This query here was the weights of the products that weren't purchased. We have that, and I will actually clean that up further. Now that we've broken it down a bit, we don't even need to have it on multiple lines. So there's my sort of pseudo table for the products that nobody's ever bought. I have that, and then I can merge those together down here, and I will just write that in. So weights of all products as, select star from weights of the products that weren't purchased. Union. This. And so then, if I want to evaluate this whole thing that I had to begin with, I can, in the same manner that I would define variables or functions for something in a programming language, I would try something like this. Weights of all products as... And there we have it. So you can see that going forward, we do have some options for working around this sort of disgusting looking massive nested query. It's also considering that building the query up from scratch wasn't nearly as hard as deciphering it once it was done. Maybe we shouldn't look too harshly on the sort of ugly syntax. But once we get going and once we begin working on assignments and things, what we'll end up with is these queries where we have this with statement with a stack of maybe 10, maybe a dozen or 2 dozen subqueries that we've given a name to. And in the same manner we would name variables or functions, we then have to combine them together. We can use one common table expression in the with statement inside of another and slowly, iteratively build up our sort of pyramid of queries until we finally get what we want. And what's great about doing it with the with clause is also that if you have the same bit of data that you have to derive more than once. And so we saw, for example, the weight of all products, the total weight of all products that were purchased. That was a query we already saw. Being able to compact it into the with clause is great because it does give us an easy way of reusing the same thing. We still have to, copy and paste it, but there is no issue of having to sort of jam it inside of a subquery nested deep down in this massive SQL construction. So starting in the next video, we're going to be writing pretty much only SQL. You should be prepared for exam number 3, of course, to write SQL and relational algebra together. And then going forward, and certainly on the next assignment, also be prepared to begin writing pretty advanced SQL and be able to maybe start with that bottom-up construction I was highlighting, where you have to, in the same manner you would in any other language, start on a big problem by solving a bunch of small problems. And what you saw at the very end there was, if you're not careful, if you end up with a massive, disgusting solution and have to take it apart, you end up having to fiddle around with syntax errors for quite a while. You notice I had to keep copying and pasting things because I was making spelling errors and I was forgetting commas, and that's one of the punishing things about SQL syntax. If you look at C or C++ or Java, for all you might not like about them, they're actually surprisingly forgiving about certain things. You can't forget semicolons, but you are allowed to have extra commas in some cases and extra semicolons and stuff. SQL is very strict, and it's sort of irrational in the way it handles stuff. And you might have noticed the word as in the with clause doesn't really make that much sense. And so it can be sort of intimidating to learn to use these things, and it's a bit of a steep learning curve. Once you have it, you can begin entering the realm of database people. Database people are the kinds of people that write queries that are pages long, that spend days in some cases writing a query. And the query can take minutes or hours to run, but it can pull together data from billions of different data points in an orderly way. And that's our goal. We want to be able to tell the database server what we want effectively.